Hello friends, welcome to Learning Chemistry. Today we will talk about an important topic from organometallics, which is isolobal analogy. So you all know that isolobal analogy is very important topic from CSIR NET, GATE and also MSc chemistry perspective. So you all know that from CSIR NET and GATE every year question comes for isolobal analogy. It is very simple topic from organometallic chemistry from where you can score 2 marks or 4 marks. So you should not miss the chance to score the opportunity of getting 2 or 4 marks, which is very vital in CSIR NET. So let's start. So isolobal analogies. First question comes, what is isolobal analogy? Hoffman, who defines the isolobal analogy in certain terms, he said that isolobal analogy is nothing but a molecular fragments which said to be isolobal if the number, symmetry properties or approximate energy and shape of the frontier orbital and the number of electrons in them are same or not identical, okay, similar. So what does it mean? So he tried to say that the two fragments which should have some property like symmetry properties or like some energies or like some orbitals or the number of electrons in them. So in this type of characteristic perspective, those two fragments should have some similarity. Based on that similarity, those fragments should be called isolobal to each other. This maybe seems to you like little bit complicated. Let me make you understand through some examples. So here you can see that there is a two fragments, one in the one fragment which is CH3 radical, so where a vacant orbital is there, where the radical electron which is placed, and other fragment where there is a organometallic compound, the Ml complex, where also an orbital where the electron resides. So these two fragments may be isolable to each other on the perspective of the free radical in their structure or maybe some electron count. So they could be isolable to each other from some characteristic perspective. So let's take an example like that. So here is a fragment which is MnCO5 and another fragment which is CH3. So how they are connected by isolobal analogy? So if you calculate the valence electron count from the MnCO5, so you know that from the Mn there is 7 valence electron present in the valence shell of manganese and 2 from each carbonyl ligand, so there is 5, so that is 10. So you get 70 electron from MnCO5 complex, and again CH3 where carbon have 4 valence electron in its valence orbital plus 3 electron from 3 hydrogen. So you get 7 electron in its valence shell of the CH3 fragment. So you can closely look at the fact that, so you can easily say that the MnCO5 complex needed only 1 electron to fill up its valence shell. CH3 fragment also needs just 1 electron to fulfill its valence shell. So from this perspective, both these fragments, the CH3 and MnCO5, they are isolable to each other by this characteristic perspective of valence electron count. So mainly in CSIR NET GATE exams, this valence electron count perspective is important from the isolobal analogy, and question comes frequently from this perspective or isolobal analogy. So let's discuss a few more examples of isolobal analogy from the valence electron count. So here you can see that there is 3 charts. So in the first chart there is a group where all of the organometallic complexes have 17 electron. If you count yourself, then you will find that they have 17 electron in their valence shell. And also the CH3 fragments, you know that they have 7 electron in their valence shell. So they are isolable to each other because both the fragments need 1 electron to fulfill its valence shell. Okay, so if you move to this group where you can easily understand that all the chromium, the molybdenum, all the tungsten, as they are in the same group, they all have similar number of valence electron count from their complexes, which is 16. So 5 to 10 from the 5 carbonyl ligand and 6 from their central metal ion valence shell, so 16 electron. So they need 2 electron to fulfill their valence shell, and CH2 fragments which is 4 from the carbon and 2 from the hydrogen, which is 6. So these two fragments also needs 2 electron to fulfill its valence shell. So from that perspective they are isolable to each other. Okay, so if you move back to this chart where FeCO5 and also their other group considered also have 18 electron in their valence shell if you count, because iron and their same group elements have 8 electron in its valence shell, and carbonyl, which have 5, from the 5 carbonyl there is 10 electrons, so total number of electrons will be 18. Valence shell is already filled up, and also there is CH3 minus, which is also equivalent to CH4, because 4 electron from the valence shell of the carbon, 3 from the hydrogen, and 1 from the negative charge, so 8. So there also the valence shell is filled up. So from that perspective, these two fragments are isolable to each other. So let's move on to some more examples from this organometallic perspective. Here I am showing the structural isolobal analogy perspective. So here you can see that there is a molecule which is Mn2CO10 and which is isolable to ethane. So how this is structurally isolable? Because the central metal atom, which is the manganese, here there is a direct bond between themselves. Similarly, in the ethane molecule there is a direct bond between the central atom, which is carbon, and they are structurally similar almost, because both the central atoms are single bondedly distributed. Between the central atom they are connected by a single bond, and around themselves there are some atoms, like for the ethane there is hydrogen, and from the manganese there are carbonyls, so they can be said isolable to each other from this perspective. And similarly, the second compound, which is osmium, so between the osmium atoms there are 3 bonds which connects them. And similarly, in the organic compounds, the acetylene and the nitrogen, they have similar 3 bonds among themselves. So from the bond formation, or the you can say the structure perspective, the osmium organometallic compound is isolable to acetylene or nitrogen. So this is another perspective which haven't come yet in the CSIR exams. So from this perspective also, the molecules can be isolable to one another. So from this list I have divided into several fragment parts. So in the first part, where there is a CH4 fragment which is isolable to their respective organometallic compound, which is nickel CO4, FeCO5. So you can calculate yourself that CH4 is central atom, which is carbon, they have octet fill up, or you can say the valence shell is fill up. So similar for the nickel, because for the nickel there is 10 electrons, and for 4 carbonyl there is 8, so 18 electron total. So their valence shell is filled up. Similarly for FeCO5 and Cr chromium CO4, so these organic compounds is isolable to CH4. And similarly for the rest of the groups, CH3 fragments, CH2 fragments, CH fragment, and C fragments. So you can do yourself to practice it, because question often comes in CSIR NET and GATE from this area. So one thing is important, that here you can see that there is high sulfur and phosphorus are written in the CH2 and CH fragments respectively. So you know that sulfur, there is 6 electron in their valence shell. So similarly, the FeCO4 in the same group, they are isolable to CH2. And similarly, they are also isolable to S, because S need 2 electrons to fill their valence shell, and also FeCO4 need 2 electrons to fill their valence shell. Okay, so similarly, both the FeCO4 isolable to CH2 fragments and also C fragments. So I hope from this point you have understood the basic concept of isolobal analogy. And the main point is, in CSIR NET or GATE, there is only the electronic characteristics from the electronic similarity or the electron count perspective of the isolobal analogies. Question comes from only that. So next we will discuss some previous year problems from CSIR NET. So let's start. So from CSIR NET December 2017, there is a question where you can see that which of the following isolobal is to CH2. So at first what we'll do, we will try to calculate the number of valence electron for this CH2. So you know that for CH2, carbon has 4 valence electron, so it is 4 and 2 from the 2 hydrogen, so we get 6. So similarly we can write 6 as 8 minus 2. Okay, so that means that CH2 fragment needs 2 electron to fulfill its valence shell. So we have to find out among these A, B, C, D, E, so which compound needs 2 electron to fulfill its valence shell. So from Cp, which is cyclopentyl ring, donates 5 electron, and after that chromium, which has 6 valence electron, there is CO2, so 2 from the each carbonyl, which is 4. So we get 15. So we can write 15 as 18 minus 3. So this is not isolable to CH2. So let's take now CpCu. So Cp donates 5 to its metal ion, and copper have 11 valence electron. So you get 16. So which can be written as 18 minus 2. So if it needed 2 electrons to fulfill its valence shell. So CpCu is isolable to CH2. Now let's check rest of the examples. So nickel, we know that nickel have 10 valence electrons, plus there is 2 carbonyls, so 2 form 2 each carbonyl, so 4, so we get 14. So we can write 14 as 18 minus 4, so 4 electron needed, so which is not isolable to CH2. Now CrCO4, for Cr there is 6 valence electron and 8 to form each carbonyl, which is 14. So 14 can be written as 18 minus 4, so which is also not isolable to CH2. So FeCO4, so you know that for Fe there is 8 valence shell electrons, and from 4 carbonyl there is also 8, so you get 16, which can be written as 18 minus 2, so it needs 2 electrons to fulfill its valence shell. So you can see that the B and E both are isolable to CH2, so this is the correct answer. So B and E isolable to CH2. So let's move on to our next problem. This has appeared in CSIR NET June 2014. So where we have question is that which of the following pair is not isolable. So A, B, C, D, there are 4 pairs. So let's check one by one. So Mn4, you know that there is 7 valence shell electrons plus 4 carbonyl, so 2 from each carbonyl, so 8. So you get 15. So 15 means 18 minus 3. So 3 electrons needed to fulfill this valence shell. Now checking for this CH3. So what CH3 needs, for carbon there is 4 electron and 3 from each hydrogen. So you get 7, which means 8 minus 1. So there is 1 electron needed to fulfill its valence shell. So MnCO4 and CH3 are not isolable to each other. So let's move on to this example where FeCO4, so for iron there is 8, then for 4 CO, for 2 from each carbonyl, so 8, so you get 16. So 16 means 18 minus 2, so it needs 2 electrons to fulfill its valence shell. So now for oxygen, you know that oxygen have 6 electrons to its valence shell, so which can be written as 8 minus 2. So FeCO4 and O, the atomic oxygen, which is isolable to each other because both needs 2 electrons to fulfill its valence shell. So next move on to COCO3, so where cobalt have 9 electrons to its valence shell plus 3 carbonyl, so 6 electrons, so you get 15, which can be written as 18 minus 3. So 3 electrons needed to fulfill its valence shell. And now for silicon is same group as carbon, so have 4 electron to its valence shell, plus there is R2Si, means each alkyl group donates 1 electron to the silicon, so you get 2, which equals to 6, which can be written as 8 minus 2. So COCO3 and R2Si are not isolable to each other. And now the last option is MnCO5, so manganese have 7 electron to its valence shell plus 5 carbonyl, so 10 electron, which means that 17 electron, which can be written as 18 minus 1 electron. So 1 electron needed to fulfill this valence shell. Now for Rs, that can be written as Rs because you can say that sulfur have, you know, similar group of the oxygen, so it has 6 valence electron plus R, which donates 1 electron to the sulfur, so you get 1 electron from that, plus 1 electron equals 7, which can be written as 8 minus 1. So MnCO5 and Rs are also isolable to each other. So the correct option which are not isolable to each other, which is the option A, MnCO4, and option C, which is COCO3 and R2Si. Okay, so you can practice it more and more, then this question is very simple and you can score easy marks from CSIR NET. So let's talk about another example. So this has appeared in CSIR NET June 2016. So we can see that which of the following pair is isolable to BH fragment. So let's calculate how many electrons are present in valence shell of BH. So boron, for boron there is 3 electrons in its valence shell plus 1 electron from hydrogen. So total you get 4, which you can write 8 minus 4. So 4 electron needs to fulfill its valence shell. So we have to find out which of the following compounds which need 4 electron to fulfill its valence shell. So let's start from Cp germanium. Cyclopentyl ring, there is 5 electron which donates to germanium, plus germanium is same group of the carbon, 4 electron to its valence shell, which is equals to total 9. So this is the electron count. So let's just count all of the metal atoms, metal organometallic compounds. So for here there is 5 for Cp, plus manganese have 7 electrons to its valence shell, 12. So let's take Cp ruthenium. So for Cp there is 5. So for ruthenium, which is similar group of the iron, they have 8 electrons, so which is equal to 13. CpCO, the cobalt, so for Cp there is 5 plus cobalt, which have 9 electrons. Okay, so you get 14, which can be written as, let's write that like 18 minus 4. So here, which is 13 minus, so 13 can be written as 18 minus 5, and 12 can be written as 18 minus 6, and also 9 is very far from 18, so it is 18 minus 99. So here you can see that the CpCO cobalt, Cp cobalt, which needs 4 electron to fulfill its valence shell, so the CpCO is isolable to beige fragments. So this is the answer. So let's move on to our next question. So this question appeared in CSIR NET June 2016. Here the question asks that which of the following pair is isolable to CH3 plus fragment. So you have to first calculate the valence electron count of CH3 plus. So 4 for the carbon, 1 from each hydrogen, so there is 3, so plus 3, and minus 1 for the positive charge. So you get 4 plus 3, 7, minus 1, which is 6. So 6 can be written as 8 minus 2. So 2 electrons need to fulfill its valence shell. So we have to find out those organometallic compound which need 2 electrons to fulfill its valence shell. So let's find out. So iron have 8 electrons to its valence shell, plus from 2 electrons to each carbon there is 5, so 10. So we get 18. So which is, so FeCO5 doesn't need any electron, which is already filled up its valence shell. So let's move on to MnCO5. So for Mn there is 7 electron to its valence shell, plus 2 from each carbonyl, so there is 5, so 10. So which means this 17 can be written as 18 minus 1. So this is also not isolable to CH3 plus. So let's move on to Cr, chromium CO5. So for chromium there is 6 electron to its valence shell, plus 2 from each carbonyl, there is 5, so 10, which is equal to 16, which can be written as 18 minus 2. So next is nickel CO3 plus. So nickel have 10 valence electron, plus 2 from each carbonyl, so there is 3, so plus 6, minus 1 for plus charge, so you get 15, so it can be written as 18 minus 3. So you can all easily understand that the chromium CO5 is isolable to CH3 plus fragment, because both need 2 electrons to fulfill its valence shell. So very easy question. So next move on to our next question. So this has appeared in CSIR NET December 2016. So this is a pretty lengthy with respect to the previous questions. So here we ask that the right fragment that can replace CO3, the cobalt carbonyl 3 in cobalt 4 CO12 is. So you can get confused that why there is two types of organometallic compounds that have been used. So you have to just take care of these fragments, because isolobal analogy only talks about the fragments or sometimes the organometallic compound itself, but in the question there is mentioned the right fragment that can replace CO3, the cobalt CO3. So you have to only take the valence electron count of this fragment, which is cobalt CO3. Okay, so let's calculate here the valence electron count of cobalt CO3. So for cobalt there is 9 electron to its valence shell, plus 2 from each carbon, which means 6. So you get 15, which means 18 minus 3. So 3 electron needed to fulfill its valence shell. So you have to check all of the option where the every compound which could be isolable to the COCO3 fragment. So I have calculated in rough that option B, which is correct. If I calculate all of the options, that will be a little messy here. So I will only calculate these 3 fragments for valence calculation. So as I have calculated a lot of electron counts from the Isolobal Analogy concept, so from option A, C and D you can do it yourself, very easy there. So just I am calculating from the correct option, which is B. So from phosphorus, you know that the phosphorus have 5 electron to its valence shell. So 5 means 8 minus 3. So also isolable to COCO3 fragments. And now from the CH fragments, so carbon has 4 and from hydrogen that is 1. So you get 5, or again, which is you can also rewrite as 8 minus 3 as previous. So now for the NiCp2, so you know that for nickel there is 10 valence electron, plus from 2Cp there wouldn't be at Cp2 because there should be Cp. It is the mistake in the question. So there is 1 Cp, so that will be 5. So you get 15. Okay, so 15 can be written as 18 minus 3. So 3 electron need to fulfill its valence shell. So all of these fragments are needed 3 electron to fulfill its valence shell. So the option B, all the fragments are isolable to COCO3 fragments. So this is the correct option. So one thing is worth mention that this is not NiCp2. This is NiCp. Okay, so this is all about the isolobal analogy with respect to CSIR NET. And GATE there is very simple questions are asked from the isolobal analogy. Okay, the CSIR NET there is some tricky questions like the atomic phosphorus or atomic silicon compounds. From these compounds you have to calculate the valence electron count. So CSIR NET isolobal analogy is very important. So I hope you understand everything from this tutorial. If you like our content, so don't forget to like and subscribe our channel Learning Chemistry, and also you can follow our Facebook page, which is Learning Chemistry. So if you have any doubt or any query about the isolobal analogy, so feel free to write in comment box. Thank you.